Hey, what's up, guys? I'm Laird. I did my 470 project here on the geolocation prompt. So yeah, without further ado, I guess I'll just get into it. So uh, basically, the idea is in order to point a sensor or uh, antenna at some target on the ground, you need to know information about where that target is and where your spacecraft is, and additionally to where your sensor is mounted. And all of these measurements have some amount of error associated with them. So in this project, we are given information about those errors and what kind of the actual true value is. And we're asked to run a Monte Carlo simulation on that. So here's the values for the knowledge error on all of these different parameters. Um, Here is kind of generally the situation. So we have our spacecraft uh, in orbit around the Earth. Let's see if I can get light more. Um, Attached to it is a sensor with some distance from the center of mass of the spacecraft, and additionally some rotation so that it is pointed at the target over here, um, which has its sight vector from Earth. Uh, and then the kind of quantity of interest is this slant range here from the sensor to the ground site. Yeah, and so essentially the model of the system, which we'll get into a little bit later, is you have these subsequent rotations and vector additions to get you into the sensor frame. And that's based on your knowledge of like your position and velocity to get the LVLH frame and your sensor mounting angles and location to get the sensor frame. And then you figure out where that kind of line of sight intersects with the sphere. And then later on, we're going to calculate the error of where that actually intersects compared to where the ground station truly is. But first, we need to kind of generally create like a Monte Carlo module in Python. And so the way we do that, so you can see here in the initialization kind of area, um, you send in a mean and a covariance as well as two functions. The first function is f, which is a function that takes your kind of state, your x values, which are all of those things that we had the errors for originally. And it takes that x, and it converts it to some output variable, some y. So in our case, that y is going to end up being, the unit vector in this slant range direction. Then you pass in that error function as well. So the error function takes that unit vector and it calculates the error between that and what it's supposed to be. So you see the inputs to the error function are the true state, the true x, the y at that x, which you calculate up here, and then or sorry, I guess that gives 0 as like just to get the size. Down here you can see the true x mu, the actual the y value you get with the like randomly modified input, and then that true y value at the mean. So that error function is going to get us our pointing error, which is that the angular distance between the unit vector and the like true line of sight vector, as well as the geolocation error projected onto the surface. You also have so in this Monte Carlo class, you have a sample method so that it just uses the NumPy multivariate normal distribution. And then to actually run the thing, the first thing you do is you generate n samples. So this method here runs the sample method n times, gets n y values, puts them all in an array, stores that as part of the object. Then you calculate the errors. So this method here runs the error function to get from the unit vector to get the pointing error and geolocation error. And then when you run it, you specify a percentile that you're interested in, and it outputs the error at that percentile. So we're interested in like the 90% geolocation error, we'd put in 90% as the P there when we run it. And interestingly, so this code is kind of agnostic to what the situation is. And so the easiest way to test it was I came up with a pretty simple case, which is just a bivariate distribution, just to kind of test more of the functionality. I didn't just do one variable, but they're both zero mean. And the first one has standard deviation 1. The second one has standard deviation 2. This is actually going to be the covariance array, so that's why it's 4 sigma squared. The model here is just y equals x. So this situation is just taking your input and passing it right through as your output. Obviously, for the spacecraft situation, that's going to be far more complicated. But for testing, our model function, we made it very simple. And then our error function is going to be the absolute value of that minus what it's supposed to be, which is based on the mean, which is 0. And so that y true term is actually going to go to 0, and the error is just going to be the absolute value of y. So what we'd expect to see is we put in this distribution with standard deviation 1 and 2, is we'd expect to see a bivariate normal distribution get spit out with the same standard deviations 1 and 2. And so what we're going to do is we're going to initialize that Monte Carlo object as our sim variable. And then we're going to run it 10,000 times. And we're going to look at the 68.26th percentile. And the reason we're looking at that percentile is that in the normal distribution, that percentile corresponds to 1 standard deviation. And so the error that we get out should be equal to the standard deviation that we put in, and that'll be stored as sig est, and it'll get printed out down here. The other thing that we do is and actually I didn't show this, but in the Monte Carlo module, I created a scatter method that'll scatter the error variables so you can see a plot. And what we see is this nice little plot over here. So we get clearly a 0 mean error. And again, we've taken the absolute value. So it's all going to be positive. We call this like a half normal distribution. And so the percentiles are actually going to still correspond to the standard deviations, but all the data that would normally be on the other side of the bell curve gets kind of flipped into the first quadrant here. And what we see is that this x scale is about half as big as the y scale. And it looks like a very large chunk is within that 2,4 kind of half ellipse there, which corresponds to the fact that the standard deviation on the y variable is greater than the standard deviation on the x variable. And yeah, as we see, when we get that estimated standard deviation, we do get 1 and 2 pretty closely. So that just gave me confidence that everything was working. Trust me, this bit of code required a lot of debugging because this is the first thing I wrote that actually used that Monte Carlo class. So yeah. But then that actually made it fairly easy to go and create the spacecraft model. So first I'm going to basically talk about, instead of this y equals x, we have a much more complicated model that spits out that unit vector. And so that model looks like this. Our input variables, again, we have our Julian date, latitude, longitude, altitude. Those basically tell us where our site vector is in our ECI. These 3 give it to us in ECEF. And then the Julian date, we can convert to local sidereal time. And then ultimately throw everything into this function down here to get our site vector in ECI. Then we use our position and velocity to get our ECI to LVLH conversion. And the reason we do that is because we know our sensor position and angles in LVLH. And so with that new DCM, we get our, we take that sensor position vector and we throw it back into ECI. So we actually have that, like where the sensor is relative to the Earth. And then we get, just based on that, what the unit vector that the spacecraft thinks based on what it knows about where everything is between the sensor and the ground site. Then what we have to do is we have to add this angular uncertainty term, and that's from like the mounting angles of the sensor itself. And again, those are in LVLH, and so we get that unit vector. And I probably could have done this a little bit more efficiently, but we bring it back over into LVLH. Add the get like what the two angles that would rotate the unit vector to its current position are, add some uncertainty to that, and then recalculate that unit vector. So now, um, you know, all of this up to here gave us like what unit vector the spacecraft thinks it should do, which might be wrong because of uncertainty in its measurements and the ground station knowledge. And then this adds uncertainty in like how the actual sensor was mounted. So even though it's like an additional layer of error that's getting added on, we convert everything back into ECI, get that unit vector, and that's what the spacecraft model function spits out. So that's our Y that goes into the Monte Carlo. Then we calculate our pointing error. So remember, this is going to actually get what the true unit vector should be. So that's going to be that d hat does. It's also going to give us what the true x is. It's just because some of the calculations require information about the state. But then the crucial thing here is that this is that y that's calculated 10,000 different times, right? So, and that's what we're trying to find the error between that and that. So the easiest one to do is just the pointing error. They're both unit vectors, so you can just take the inverse cosine of the dot product. That's this line here, and that goes straight to our output. But the geolocation error is a little bit more difficult because what we're doing is we're trying to calculate the intersection between that vector and the sphere of the Earth. So the first thing we do is we are going to calculate the radius of the Earth at that point. And the point we're going to use is just at the actual location of the ground station because we're going to assume it's not super far off that there's going to be a huge difference. So we get the lat long alt from our like true state, and we calculate the radius of the Earth at that location. Then we this is all in like the background slides that Dr. Mehiel provided, so I didn't really get into the details here, but or at least I won't in this presentation. But there ends up being like kind of a quadratic formula, and so there's different cases depending on the sign of the discriminant. So the first thing we do is we calculate that discriminant, and again here we use the actual value of what the unit vector should be to get that discriminant. If the discriminant is less than 0, then you're going to have complex solutions, and those don't correspond to a real like intersection. So we'd output not a number. If it's 0, it's tangent. It's probably never going to happen exactly like that, but it's in the code just in case. And otherwise, it's the minimum of those two like plus or minus values. The reason it's the minimum is because that corresponds to the shorter distance. The longer distance obviously would be going through the Earth, which doesn't, again, correspond to an actual solution. So from that, we get those p-values, and those are the scalar slant ranges. And then we find the vector that goes from the center of the Earth to the point on the surface where our like line of sight intersects. That's that t. And again, we have our desired, which is the truth value, and then our actual one given the random inputs. And so our geolocation error is just the difference between those two vectors, between t-act and t-des. But we don't just want that difference necessarily in ECI. We're going to want it in some topocentric coordinate frame. And that's because obviously the Earth is curving, and so like some error is actually going to like get projected down onto the surface. And so we're going to convert from that ECI difference into southeast zenith coordinates. And then that's going to give us our geolocation error. And so we're going to actually output the geolocation error vector, but then we're also going to output the magnitude of that geolocation error. And then the actual output, the like E or whatever, I'm not sure if I really defined that earlier, but the output is just going to be this like a single vector that has the pointing error, the magnitude of the geolocation error, and then the actual like northeast zenith geolocation error. Yeah, so lastly here in the code, we got to talk about the way we're initializing the simulation. So we are given all of these at like true values and then the standard deviations. We run through all of that and then we put it in one big basically mean vector and covariance vector, which I guess got cut off on the bottom here, but it's just kind of stacking all those diagonal matrices together for those covariance. And then it's just a single column vector for all the true values. We create that Monte Carlo object and we run it 10,000 times, and this is what we get. So on the Earth's surface, we get about 150 meter spread east-west, and like a 10-15 meter spread north-south. Obviously, again, centered at 0, 0. Our pointing error is very, very, very small, but because we're hundreds of kilometers away, that still corresponds to a 90th percentile geolocation error of 70 degrees. This actually goes down as we increase in altitude. So when we run this at higher and higher altitudes, we see that we actually lose a lot of that high geolocation error, although it does level out kind of around 50 meters. Additionally, we can look at the effect of each parameter. So what we see here is the thing that has the biggest effect is the target location knowledge. We know our target latitude and longitude to 10 to the minus 4 degrees on the Earth's surface, but that still corresponds to quite a large physical location shift. And so that gives us that like 47% or 47 meter contribution to our geolocation error. And then elevation is also similar. Similarly, like it's a pretty important effect. Because of the curvature of the Earth, if you think something's higher or closer in, then you actually end up missing by more than you are off in your elevation. Now, the other thing to note here is that the root sum square of all of these errors is 56.3 meters, which is significantly less than we were seeing over here. And the reason for that is that at least a couple of these big ones were fairly correlated. In particular, I think just the way that the like on the surface of the Earth, the target and the spacecraft, like that geometry meant that like these two errors, the elevation and the longitude, ended up mostly happening in the same direction, which was that east-west, which is why like the east-west side of this range is such a wider range than the north-south. But I'm not 100% sure why that root sum square was so much lower. Or like I guess why those were as correlated as they were. But the correlation caused the root sum square to be lower. Yeah, so that's all I've got. Hopefully this wasn't terribly long, but thanks for watching. That's my cat.